Download this code from codegive.com, link in the description below. OK, creating a complete operating system from scratch in a single 7-hour tutorial is a monumental task. It's simply impossible to cover every single detail and nuance in that time frame. However, I can give you a high-level overview, break it down into logical steps, and provide code examples, mostly in C, as that's the dominant language for OS development, that will get you started on the journey. Important considerations ****Scope** will focus on building a basic kernel. This means memory management, basic process management, simple device drivers, and a rudimentary shell. We won't cover a GUI, networking, or advanced features. Time commitment ** building a real OS takes months, or years, of dedicated work. This tutorial gives you a solid foundation, but you'll need to continue learning and experimenting. Target architecture * I'll assume you're targeting x86 architecture, the most common for personal computers. The code will be optimized for simplicity and understanding, not necessarily performance. Assembly language * You'll need a basic understanding of x86 assembly language, as it's essential for low-level tasks like booting and interrupt handling. Compiler * You'll need a cross-compiler. I recommend using GCC for x86 ELF development, example i686 ELF GCC. This will allow you to compile code that runs on bare metal, without relying on an existing OS. Bootloader * You'll need a bootloader to load your kernel into memory. We'll use grub, GNU Grand Unified Bootloader, for simplicity. Grub will load the kernel and jump to its entry point. Emulator / virtual machine * You'll need a way to test your OS without risking damage to your main system. QEMU is an excellent and free emulator. VirtualBox or VMware are also options. Hindi overview. 7. x86C. Let's begin. Phase 1, setting up the development environment, 30 minutes. 1. Install the cross-compiler *. 2. Install QEMU *. 3. Create project directory *. Phase 2, the bootloader, 30 minutes. We'll use grub to load our kernel. 1. Create grub.cfg *. This file tells grub what to load. 2. Create directory structure *. Phase 3, the kernel entry point, 1 hour. 1. Kernel.c *. The main kernel source file. 2. Linker.ld, linker script tells the linker how to arrange the code in memory. 3. Makefile * automates the build process. 4. Build and run *. This will compile the kernel, create an ISO image, and run it in QEMU. You should see my OS is running, printed on the screen. This is writing directly to the VGA text buffer. Explanation ***. Kmain, ***. This is the kernel's entry point, similar to main, in a C program. It writes a string to video memory, address 0xb8000, which displays it on the screen. Linker.ld The linker script tells the linker where to place different sections of the code in memory. Entry, kmain, specifies the entry point. Equals 0x100000 loads the kernel at address 0x100000, 1 megabyte. Makefile * The makefile automates the build process, compiling the C code, linking it with the linker script, and creating a bootable ISO image. i686 ELF GCC * The cross-compiler compiles the C code into machine code suitable for x86. Asterisk nost lib nost in asterisk these flags tell the compiler not to use the standard C library or include standard header files. We're building an OS from scratch, so we can't rely on these. Asterisk no built-in asterisk disables built-in functions like mempp, which are often provided by the compiler. Asterisk QEMU system i386 asterisk the QEMU command runs the ISO image in an emulated environment. Phase 4, Basic Memory Management, 1 hour. We'll implement a very simple frame allocator. This is how we allocate and deallocate physical memory. 1 memory.h asterisk. 2 memory.c asterisk. 3 include in kernel.c asterisk. Explanation asterisk. Asterisk frame allocator asterisk we manage physical memory in units called frames, pages. A bitmap tracks which frames are free and which are in use. Asterisk initialize underscore memory, asterisk sets up the memory manager. It calculates the number of pages and initializes the bitmap to indicate that all pages are free. It also places the bitmap after the usable memory. Asterisk allocate underscore page, asterisk finds a free page, by checking the bitmap, marks it as used, and returns a pointer to the start of that page. Asterisk free underscore page, asterisk marks a page as free in the bitmap. Asterisk memory underscore start asterisk the address where the kernel and allocated memory will reside. Asterisk page underscore size asterisk the size of a memory page, 4096 bytes. Asterisk bitmap asterisk a bitmap is a memory efficient way to track the status of multiple items, in this case, memory pages. Each bit in the bitmap represents a page, 0 means free, 1 means used. Important notes asterisk. Asterisk this is a very basic memory manager. It doesn't handle fragmentation, error checking, or other advanced features. Asterisk in a real OS, memory management is far more complex, involving virtual memory, page tables, swapping, and more. Phase 5, Interrupt Handling, 1 hour. Interrupts are how hardware devices, and the OS itself, signal events to the CPU. 1 idt.h asterisk. 2 idt.c asterisk. 3 Israel S, assembly file for interrupt handlers. 4 irq_handler.c. 5 update kernel.c asterisk. 6 update makefile asterisk. Explanation asterisk. Asterisk interrupt descriptor table, IDT a table that maps interrupt numbers to interrupt handler routines. Asterisk IDT underscore entry underscore T asterisk structure that defines an entry in the IDT. Asterisk IDT underscore PTR underscore T asterisk structure that the CPU uses to locate the IDT in memory. Asterisk IDT underscore set underscore gate, asterisk sets up an IDT entry, specifying the handler's address, selector, and flags. Asterisk IDT underscore install, asterisk loads the IDT into the CPU using the lit instruction. Also enable interrupts with ST. Asterisk ISR0 and ISR1, in Israel S these are interrupt service routines, ISRs, written in assembly. They save the CPU state, call AC handler, IRQ underscore handler, and restore the CPU state before returning from the interrupt, IRET. Asterisk IRQ underscore handler.c asterisk this is the C function that gets called by assembly-based interrupts. It's where you'd handle the interrupt. Important notes asterisk. Asterisk this is a simplified interrupt handler. Real-world interrupt handlers need to acknowledge interrupts to the interrupt controller, PIC or APIC. Asterisk interrupts can be a complex topic, especially when dealing with hardware interrupts. Phase 6, Basic Process Management, 1.5 hours. We'll create a simple process table and a basic process creation function. 1 process.h asterisk. 2 process.c asterisk. 3 example process function, a very basic process. 4 update kernel.c asterisk. 5 update makefile asterisk. Explanation asterisk. Asterisk process table asterisk processes is an array that holds information about each process. Asterisk process underscore t asterisk structure that defines a process. It includes the process ID, stack pointer, ESP, and instruction pointer, EIP. Asterisk initialize underscore processes, asterisk initializes the process table, marking all slots as unused. Asterisk create underscore process, asterisk creates a new process. Asterisk finds a free slot in the process table. Asterisk allocates a stack for the process using allocate underscore page. Asterisk initializes the processes ESP and EIP. The EIP is set to the entry point of the process, the function where the process will start executing. Asterisk switch underscore process, asterisk implements a rudimentary context switch. It saves the current process's state, ESP, and restores the next process's state. The IRET instruction is not used here as it is not a true interrupt-based switch. A dummy inline assembly context switch implementation is performed. Asterisk process underscore example, asterisk a very basic example process that loops forever. Important notes asterisk. Asterisk this is an extremely basic process manager. It lacks many features found in real OSs. Asterisk no scheduling asterisk the switch underscore process function just cycles through the process table. A real scheduler would use algorithms to choose which process to run based on priority, etc. Asterisk no protection asterisk processes can access each other's memory, which is a security risk. Asterisk no inter-process communication, IPC processes cannot communicate with each other. Asterisk a proper process management system involves virtual memory, page tables, and more sophisticated scheduling algorithms. Asterisk the current implementation of switch underscore process is quite basic and doesn't save all the necessary registers. Phase 7, Device Drivers, 1 hour. We'll implement a simple driver for the serial port, COM1, for output. 1 serial.h asterisk. 2 serial.c asterisk. 3 update kernel.c asterisk. C. / kernel.c. Include memory.h. Include idt.h. Include process.h. Include serial.h. Extern void process underscore example. Void kmain. / initialize memory, assuming 16 megabytes. Initialize underscore memory, 16 asterisk 1024 asterisk 1024. / initialize idt. idt underscore install. / initialize process table. Initialize underscore processes. / initialize serial port. Serial underscore initialize. / create a process. Int PID equals create underscore process, uint32 underscore t, process underscore.